we're now going to consider how velocity and acceleration are related in general when an object moves in two dimensions. We're going to take this blue curve right here to be the path of an object moving in the xy plane. And we're going to first show that the velocity vector must be tangent to this curve. The velocity vector, of course, is just the derivative of the position, which means the x component of the velocity will simply be the derivative of x with respect to time, and the y component will just be the derivative of y with respect to time. The tangent to this curve will just be the derivative of y with respect to x. But that will simply equal the ratio of the y component to the x component of the velocity, because if we take dy dt and divide it by dx dt, the dt's essentially cancel out, and we end up with dy dx, which is the tangent to the curve. Now, vy over vx will also give us the direction of the velocity vector, which now must be tangent to the curve. Next thing we want to consider is the acceleration, which of course is just the derivative of the velocity. However, considering the x and the y components of the acceleration will not prove to be that convenient. So instead, we're going to break the acceleration vector, which will be given by this green arrow right here, into two different components. Rather than x and y, we're going to break it into a component that is in the same direction as the velocity, and one which is perpendicular to that direction. Now, in this particular example, the tangential acceleration, which is what I've labeled a sub t, is in the opposite direction as the velocity vector. That means this will be an object that will be slowing down because the acceleration is in the opposite direction as the velocity. Second component we're going to call the radial component, and while the tangential will cause the object to speed up, or in this case slow down, the radial component will cause it to turn. And the radial component will be perpendicular to the velocity, or perpendicular to the tangential component, but it'll also always be pointed in towards the center of the turn for the path. So it has to point down here to make the velocity vector turn in the direction of the curve. To see that a little more clearly, we'll get rid of some of this clutter and note that the new velocity will equal the old velocity plus the change in velocity. And the change in velocity is just the acceleration times some time interval. And that'll be a vector which is parallel to this vector right here. So this is the change in direction. And we add that to the old velocity vector, and the resultant of this vector sum will be this line right here. And this will be in the direction that the object must be moving to stay on this blue curve. If the radial acceleration were pointing towards the outside of the curve rather than the inside of the curve, this little vector right here will be pointing in the other direction, and the vector sum will be going in the wrong direction and would not keep the object on the curve that it's moving in. So to be consistent, the radial component must be pointed towards the inside of the curve to keep the velocity vector pointed tangent to the curve. About the only thing we really need to worry about with this sort of general and kind of abstract concepts is that once you know the curve that a path the object is traveling, you know a little bit about the velocity vector and the acceleration vector. So consider this example right here. Here I've got a different path. I've got an object that's moving in this direction right here. And consider point P right here. Just based on our definitions of velocity and acceleration, we can say something about what the velocity and the acceleration vectors must be. And I've got four options right here. So what I want you to do is just consider those four possibilities and tell me which one of those must be true. Now, one thing we can definitely say is option number 2 must be wrong, because while the velocity is pointing in what appears to be the correct direction, this says the object is not turning, because the acceleration is just parallel to the velocity. Well, it must be turning because the curve is, it's curved. It's not a straight line. So This can't be right. This one right here also can't be right because it's pointing the acceleration away from the center of the curve and will make the object turn upward when it's actually turning downward. So this one must be wrong. This one right here has got to be wrong because the velocity is pointed in a direction other than the tangent to the curve. In fact, this one kind of looks like the velocity and the acceleration are backwards, because the correct answer is this one. The velocity is tangent to the curve and the acceleration points towards the inside.